I went back and I redid my notes from Wednesday. We're going to fix the debacle that was me trying to demonstrate the importance of partial fugacity. Because partial fugacity is the whole reason why we even have fugacity. We don't need it for single component systems. We need it for multi-component systems. So I think it is important to go over why this is a property that we care about. So for phase equilibrium, in multi-component systems, which is basically everything that chemical engineers care about when it comes to thermodynamics. Distillation, crystallization, flash separators, right? That is the bread and butter of chemical engineering. There is no other discipline that does that like chemical engineers do. So if you are going to earn your paycheck as a chemical engineer, this is one of the single most important issues. The function that we have to calculate to know whether or not our system is in phase equilibrium is the partial molar Gibbs free energy of species I is going to be constant across all of the phases. This could be solid liquid, solid vapor, vapor liquid, right? This could be liquid liquid. This is the property that we want to calculate for determining phase equilibrium, which is really one of the cornerstones of chemical engineering. For any partial molar property, this is a defined principle, but of course, thermodynamics has been developed over hundreds of years. This partial property, the partial molar property, was defined very cleverly such that this result is manifested, right? It wasn't defined arbitrarily and then all of a sudden it worked out so conveniently. No, it's through trial and error. This is the framework that people have established. So what the partial molar property is telling us is how does the total system property, in this case it could be Gibbs, change when I change the composition, right? So the phase equilibrium is determined by how much is the rate of change of the Gibbs of the vapor versus the liquid as you change the composition a little bit for moving and subtracting component I into the system. Now we do this process at constant temperature, pressure, and holding the number of moles of everything else constant in the system. So for the partial molar Gibbs, I'm just going to drop the nj not equal to I, just for the future of this. Just note that, of course, this is a partial derivative, so if we're changing ni, then of course we have to be holding everything else constant. So just for convenience, I'm not going to write that anymore. Right, so we can write this as the partial derivative of the Gibbs free energy of a mixture, which is a function of temperature, pressure, and composition here. We can substitute in our definition for Gibbs. We can evaluate this expression and find that the partial molar Gibbs, which is the most important partial molar property that we're trying to calculate here, is going to be related to the partial molar enthalpy and the partial molar entropy, right? We're just distributing this derivative here. We're holding temperature constant, so we don't have to do the product rule or anything like that. This is also equal to how is the slope changing of the enthalpy of the mixture and the entropy of the mixture. Right? That's effectively what we care about. What is the rate of change of enthalpy differences when I add and subtract a little bit of component I? What is the entropy changes when I add and subtract a little bit of component I? Right? So the phase equilibrium is not related necessarily to the total Gibbs of the system, but rather the rates of change of enthalpy and entropy as you modify the composition of the fluid. So we can write then that the Gibbs of the mixture, so G underbar, is going to be equal to the summation of the partial molar enthalpies minus the summation of the partial molar entropies. And this is sort of leading us into what I tried to do on Wednesday. I would say I was about 30% successful. So we're going to plot out, again, the enthalpy of the mixture, which is a function of temperature, pressure, and composition. And let's see if my blue marker is any good. So for any arbitrary mixture, let's just say it's endothermic. And for the most of this, we'll just kind of ignore the enthalpy. But let's say it's an endothermic mixture. This point right here, x of A is equal to 0, x of A is equal to 1. We can have units here of kilojoules per mole. When you times temperature and entropy, this also comes up with kilojoules per mole. We have a positive delta H of mixing. Delta H is greater than 0. That would be for an endothermic process. If it's an exothermic process, then effectively you know the two fluids are more or less going to be infinitely miscible, or miscible because, unless you have a really strong entropic reason why they don't want to mix. If it's exothermic, it's really energetically favorable. So the endothermic mixtures are really where it's a little bit more interesting in terms of the thermodynamics. Entropy, the TS contribution, for an ideal gas mixture will look like this. In this case here, this is going to be for an ideal gas mixture when I'm plotting out. So in this case, we are generating entropy in the process of mixing, which means that it is going to be favorable. Sorry, this is the minus TS contribution. So the Gibbs free energy is going to be the black line plus the blue line. If it goes up, the Gibbs free energy of the mixture is higher. If it goes down, the Gibbs free energy of the mixture is lower. The system will always tend to go to equilibrium at the lowest Gibbs free energy. So if we were to look at any individual spot, whether or not the system phase separates is going to more or less determine on whether or not it's going to be above or below the line. So let's look at the entropy a little bit more, because it's going to be the more interesting of the two components. So we are going to model the delta S of mixing for this process as an ideal gas mixture, which is the simplest expression that we can come up with for mixing two fluids together. So that means that the entropy of the system, in this case, this is just by definition, is the mole fractions multiplied by the partial molar properties. Where for an ideal gas mixture, this is simply equal to the entropy of the pure component minus the contribution that we derived this week for the ideal gas mixture. So what we will do to simplify our lives is that we will set our reference states as the pure component at the temperature and pressure that we are mixing this system. So when we mix it, we'll mix it isobarically, and we will mix it isothermally. That makes our lives a lot simpler, because that means our reference state is the pure mixture, pure fluid properties, right? S under bar sub I, which tells us this is the pure fluid property according to the notation that the Sandler book has adopted. But of course, when you translate from book to book, the notation will be slightly different. So that tells us that the entropy of the mixed system, right, notice that there's no subscript here, is equal to minus R summation of this term here. So what we want to know what happens to the partial entropy, and then consequently the partial Gibbs, as we approach dilute systems. Because the most important thing to remember here, right, is that the phase behavior, the partial molar Gibbs, is determined by the rates, the relative rates of change of enthalpy and entropy as you change the composition of the system. So, one thing to note here. I'm going to do a little bit simplified math. It is not 100% correct. But as we take the limit as x of A, or the number of moles of A goes to 0, I believe the math should hold true. But strictly speaking, if I were to look at the definition of the partial molar entropy, right, which is the rate of change of the entropy as I add or subtract a little bit of species I, this is not equal to how it changes with respect to mole fraction. But as n of A goes to 0 and x of A goes to 0, those differences should more or less be kind of washed out. But strictly speaking, what I'm going to do next is not thermodynamically accurate mathematically. But it illustrates the conclusion in a much, much simpler way. Just so we're on the same page. So let's evaluate what the partial molar entropy is, but substituting in our ideal gas mixing relationship here. So let's say this is approximate. All right. This is our expression for the entropy of the mixture. We're taking the partial derivative with respect to xi, saying how does this, effectively we're saying how is the slope changing at the limited cases. So what we'll do is for an AB mixture, right, we can rewrite this as minus R x of A Actually, I took the derivative of my notes, I took the derivative before I substituted it in. Let's hold off on this for 1 second. We can actually evaluate this pretty trivially. So let's just evaluate this first here. So this is minus R d dxi at constant temperature and pressure. We just have to use the product rule here. So minus R times by the summation of first times the derivative of second. So that's R times 1 over xi. Second times derivative of first plus xi. So far, so good. Now we substitute for an AB mixture. So this cancels with this. We have 1 plus natural log of x of A plus 1 plus natural log of the mole fraction of B. So let's take the limit of the partial molar entropy as the mole fraction of species A goes to 0, in which case this will be equal to what is the natural log of 1? Goes to 0. What is the natural log of 0? Minus infinity. Minus r times minus infinity. That tells us that the partial molar entropy of A at x equals 0 is equal to infinity. Which means that when we put it into our Gibbs, goes to, the partial molar Gibbs goes to negative infinity as the dilution gets close to 0. So if we go back to our chart here, what that is saying that the partial enthalpy is proportional to the slope as x goes to 0, and that the partial entropy here, in this case this is Ts over bar of I, is proportional to the slope. In this case it is negative infinity. And in the case of enthalpy, this is always going to be less than infinity. If the slope here were to be similar to the entropy curve, it would effectively mean that the two fluids, A and B, would have to be infinitely repulsive. So it would take an infinite amount of energy in the universe to squeeze two molecules closely together. So in this case here, enthalpy is never going to overcome the entropic contribution to the Gibbs free energy, or the partial molar Gibbs free energy, which is what we care about for phase equilibrium. So what that means is that even in the simplest of calculations that we have, in order to calculate phase behavior, assuming your vapor phase behaves as an ideal gas, the one variable that we care about for all of this business with partial molar properties is undefined, right? So instead, what we do is we define a new function. Let's see, there's still this part over here. We define a departure function. And this is something that you hopefully should have seen in homework 2 as well. Right? When you calculate the entropy departure function for the van der Waals fluid, if you didn't evaluate that expression continuously through, you would have found that you'd have either like some sort of a positive infinity or a negative infinity. Does that sound familiar in the homework? But the departure function eliminates that effect when you're calculating it with respect to entropy. So what we do is we define a property called the partial molar fugacity. Sorry, partial fugacity, it's not a molar property. And we can show that the partial fugacity of phase 1, phase 2, to an arbitrary number of phases holds true at equilibrium. So it'll have exactly the same properties as the partial Gibbs. And how we define it then is just a Gibbs departure function that is scaled identically to fugacity. In fact, fugacity is defined based on the partial fugacity. Right? This is what we've done. That is what we care about. It's just defining the partial fugacity, because all of the discontinuities that exist in entropy of mixing are contained within the Gibbs of the ideal gas mixture. Now further, we can also show that the difference between the Gibbs partial fugacity and the ideal gas mixture's Gibbs partial fugacity can be related to volume changes. 0 corresponds to the ideal gas state, P corresponds to the real state. This is an isothermal path. This is just the evaluation of the combined first and second laws of thermodynamics, but following an isothermal path and defining a partial Gibbs departure function. One last step that kind of wraps up where I wanted to get to on Wednesday, hopefully in a more coherent fashion. Is we can get access to this information from an equation of state. And this is one of the equations that was on your sheet that I handed out yesterday. So you already have access to it. Right, so this is a common way that we can write this. This is the partial fugacity coefficient. Right, where we just scale the fugacity in terms of what the system pressure is. So this partial fugacity coefficient varies plus or minus around 1 a little bit. Just a convenient way to simplify this. So we can write this by substituting in the ideal gas law and a real fluid equation of state here. So, partial Gibbs controls phase equilibrium. Partial Gibbs is an undefined function. So what we do is we remove the undefined contribution to the partial Gibbs by scaling it with the ideal gas mixture. That defines for us the partial fugacity. The partial fugacity can be calculated from an equation of state. Now the only term that we now need to evaluate, right, so hopefully everyone in homework 2 should have had some experience playing around with this. Well, not this one exactly, but for the pure component system. For a multi-component system, we need something called mixing rules, right, which basically tells us how does species I interact with species J, interact with species K, interact with species M, interact with species L. Right? So with an equation of state, we can modify our equation of state to introduce a multi-component mixture, and I'll show you how to do that probably on Monday. But now we have a means to calculate the partial Gibbs to do phase equilibrium calculations. And this is what I meant to present on Wednesday. But I wanted to go over it again because this is a very important contribution. This is basically the cornerstone of multi-component, multi-phase thermodynamics. And it goes back to the notion here that there is no fluid mixture that is so repulsive that the entropy gained by mixing those two is overcome by their repulsion. So no matter how much two fluids hate each other, they will always be miscible, at least to some extent. So if you were to plot the Gibbs free energy of this system, you will always have a small dip on either side. Now the problem is, thermodynamics will basically, from this point on in the class, will break down to a numerical methods course. We have effectively defined the last property here that we care about. I'm sorry, there's one more, activity coefficient. But everything that we're doing now is just defining these terms and setting up a system of equations. So some of the challenges associated with modern thermodynamics is not actually developing new theories, which some people are doing that, but rather is in developing practical implementations to find really, really, really small regions like this in a really big system. So reservoir flow simulators is an extremely common area where you might have a trace amount of water or a trace amount of oil in the water, or you might have a small amount of vapor phase forming, which can have a significant impact on the flow characteristics, particularly if you have an oil-wet rock versus a water-wet rock. So you want to know which is the two dominant phases. But it's hard to find this small region, which may be less than, let's say, 10 to the minus 4 mole fraction. Which means that I've got a reservoir that's a couple of cubic kilometers. I've broken it down into little voxel box sizes, maybe on the order of centimeters to meters. So I have millions and billions of nodes. And at every single one of those nodes, I need to calculate what the phase of that node is based on the temperature, pressure, composition, and flow from the previous time step. Then I have to solve a system of equations to calculate the partial fugacity from an equation of state, which involves a very unpleasant derivative, or integration. And my numerical method doesn't want to be searching in this area here in teeny little time steps of 10 to the minus 4 to find the minimum Gibbs free energy or where the fugacity is equal. So it's very challenging to implement this in a real practical situation. So that's one area where it's really, numerical methods is a really kind of modern area for looking into this. But there's also people developing new equations of state, very clever equations of state that kind of rely on molecular simulations tuning the equations of state as opposed to kind of guess and check work. Any questions? This is going to be our goal from here on out for classical thermodynamics, is to evaluate this function right here, or to find experimental data that will inform us on this. We're going to touch a little bit on chemical reaction equilibrium. The problem with chemical reaction equilibrium is unless you do only ideal gas mixture chemical reactions, it's not that much different from phase equilibrium itself. Big, complicated, lots of equations. All right, so let's go and do a really quick overview of where we have gotten, how we got here, and what are the tools that we have in our arsenal, and then we'll start to talk about how do we actually calculate these real things. So I've tried many ways to come up with a good visualization method for this, and this is the best that I've come up with so far. So if I were to build a graph here, this is conceptual, of course. So in my chart of thermodynamics, up here I have a real, pure, single component material. Here I have a real mixed system. Here I have an ideal mixed system. So our notation is that we have properties of the fluid that are a function of temperature, pressure, and composition. Right, this is the notation that we use for the total mixture. Or sorry, rather, this is for a pure component, so it is, we include a little subscript I to remind us that this is potentially going to be in a mixture. When we mix it, the property that we care about is getting the partial property with the overbar. This is saying how this real fluid behaves in the mixture. Right? This is what we want to calculate for Gibbs so that we know the phase equilibrium.
The pure property is function of composition?
Well, yes, I suppose technically yes, but that composition is 1, so we can get rid of that. If we go to an ideal system, the simplest that we have is going to be temperature and pressure. Sorry. Theta, so any property, ideal gas, easy to calculate. That's why we like ideal gases. But what we can also have is we can go along the middle path here, where we have the partial molar properties of what we call an ideal mixture which is basically saying I take a real fluid with real sort of non-ideal properties, and then I mix it. But the way that it gets mixed is following an ideal mixture, meaning that the ideal gas follows, sorry, the mixing follows ideal gas mixing, and the enthalpy of mixing is actually going to be 0. We can also have, lastly, the simplest system that we can come up with is an ideal gas mixture, which is a function of temperature, pressure, and composition, right? So I've plotted out the entropy of an ideal gas mixture. In this case, the enthalpy here is not an ideal mixture because there's heat being released or consumed. It's an endothermic. In this case, it's an endothermic system. Now, there's one thing that we'd like to eliminate, and that's this right here. This entropy of mixing, even for an ideal gas mixture, is unpleasant. Right? It involves a relatively complex function, right? Xi, natural log of xi. Taking the derivatives is a little bit tedious. So instead what we do is we define something called an excess property. So for any arbitrary function, we'll write this as theta excess. So instead of it being the actual, let's say, Helmholtz, or the actual Gibbs, or the actual volume, we'll call it the excess volume. And how we define this is we take the change of the property in mixing of the real fluid minus the change in mixing of an ideal mixture. So it's not the change upon mixing, but it's the change of ideal mixing for the real property. Because the idea here, this is going to be what I'll call easy to calculate. We've already derived the set of rules to understand how ideal mixing occurs, and it's effectively this blue line right here. That's the ideal mixing entropy curve. So what we want to do is when we talk about systems that are interesting and new, we actually really only care about what is the deviation of the mixing from the ideal mixing behavior. And that is where all of the information is contained on how this fluid is going to behave uniquely compared to a simple, dumb, ideal gas mixture. So if we take this definition, we know that the delta V of mixing is then just going to be equal to, oh, sorry. Okay, so in the case of volume, enthalpy, and internal energy, the delta V of mixing is just equal to the excess volume. The delta H of mixing is equal to the excess enthalpy. And the delta U of mixing is equal to the excess property, because we have no volume change, there's no energy change, there's no enthalpy change for an ideal mixture. So for these three properties, nothing changes. However, with entropy, there is always some value for delta mixing, even for an ideal mixture. So for S, G, and A, we have slightly different properties, and this is just algebra substituting in our ideal gas mixing for entropy into our definitions. Okay, so the objective here is that we're also further eliminating all of this mathematical complexity. So, I mean, if you subscribe to the school of thermodynamic thought, all of this math is intended to make our life easier. But let's recap to how we've gotten here. So effectively, what we've done is we've taken the first and second law of thermodynamics. We've taken that to define Gibbs. We've used Gibbs to define phase equilibrium. We've created an arbitrary new function called the partial molar property. Then we've taken that partial molar property, we figured out basically and defined a fugacity function. Further, we've taken the Gibbs, not only of mixing, then we've defined a new function, which is the deviation of that function from mixing, and that's how we've gotten to the excess Gibbs. So it's really a definition on a definition on a definition on a definition on a definition. But it's useful. And this is what we do. So unless you want to rewrite all of thermodynamics for the past 200 years, you're going to have to just accept the fact that it's a little bit confusing. But remember that this still contains all the information that we need to know. We don't actually have to calculate the Gibbs. We don't have to calculate H. We don't have to calculate S. All we need to calculate is the excess Gibbs, or rather the partial excess Gibbs, which makes it even more fun. So if we take all of this information and we substitute it basically into our definitions here of fugacity, we do a tedious amount of relatively straightforward algebraic manipulation, which I think I have clearly demonstrated I do not have an aptitude for. We can write that the partial excess Gibbs, right? So effectively what we're doing here is we're defining the partial excess Gibbs as taking the partial derivative of the excess Gibbs with respect to changing the composition a little bit, because that's the only thing we care about. And we can substitute all these kind of expressions and manipulate it a little bit, and we can come up with we can relate it to the fugacity. So what we're saying here is that the partial fugacity is effectively looking at the difference as how the fluid behaves as a real component compared to how it behaves in a mixture, which we can get from an equation of state telling us the difference of how the fluid behaves in the mixture versus how it behaves as a pure species. These are all just definitions. So this expression here For a low density fluid, basically a gas, or something that's far enough away from a critical point along those lines, we can evaluate this straightforward. So if you go in your book, you look at chapter 9, Professor Sandler has already kindly evaluated these expressions for various equations of state. So the only challenge then in thermodynamics is to code this into a multivariable solver, saying that if I have, let's say, an A-B mixture, right? I'm going to have an excess Gibbs of A in the liquid phase, I'm going to have an excess Gibbs of A in the vapor phase, I'm going to have an excess Gibbs of B in the liquid phase, I'm going to have an excess B in the vapor phase. I need to solve this equation such that the excess Gibbs of A and B cancel each other out. The partial excess Gibbs. So all of thermodynamics then, because someone's already gone through the mathematics of evaluating this function for a particular equation of state, is just a matter of substituting in the right constant properties for that material and then evaluating this system of nonlinear equations. But MATLAB can do that, Python can do that, Excel can do that, everything can do that. However, for a dense fluid, i.e. a liquid or something that is approaching its critical point, or a really, really concentrated or really, really dense non-ideal fluid, vapor phase rather, it does not work well. Equations of state are, in general, as a good rule of thumb, very bad when it comes to predicting liquid phase properties, particularly compressed liquid properties. And this is where all of the elegance and effort in thermodynamics falls apart. Because, as it turns out, this term here is very, very difficult to calculate. So what we do is we define something called an activity coefficient. So the activity coefficient is defined as, and typically I'm putting an L, this is most generally used for the liquid phase, because for the vapor phase, an equation of state is typically good enough. And we can also write, I'll just rearrange this equation here just quickly. And this is related directly to the partial Gibbs. These are going to be something we're going to play around with for basically the next few weeks. Okay. So unfortunately, what we've done is we have very elegantly worked ourselves into a corner where we have thermodynamically demonstrated that if we can calculate this property, the partial fugacity, then we can solve all of our problems. But the challenge is we can't actually calculate our partial fugacity for a liquid system. We can, but it's only an approximation. In general, it's not particularly accurate unless it's for a relatively simple system. So the equations like SRK and Peng-Robinson, those were developed in the 1970s and 80s by oil and gas companies to optimize refineries, reservoir simulators, distillation processes. Vapor-liquid equilibrium for hydrocarbon mixtures is relatively straightforward. So these ones are actually not too bad. But when it comes to heavier hydrocarbons, they had to introduce more complicated equations of state. But for the volatiles in crude oil, and relatively low molecular weight materials, right? Maybe naphthalene, decane, and below. Those equations of state are great. They work really, really well. But for any sort of really highly non-ideal mixtures, things with water, strong permanent dipoles, hydrogen bonding, no equation of state is really generalizable. You can have really optimized equations of state, maybe for a water ammonia system, for example. Right? Someone can develop a dedicated equation of state for a small subset of systems, but that subset wouldn't be applicable if you took it from a really polar mixture to a really non-polar mixture. Right? You'd have to re-optimize everything. So instead what we do is that we introduce something called an activity coefficient, and there's a number of approaches to accomplish this. So with the activity coefficient, some people will say, okay, let's assume the molecules mix in a particular way. What is the functional form that the activity coefficient should have? And maybe it has some e to this or whatever the case is, and then they just tune the parameters. So what we do and what we'll be talking about next week is assuming fluids behave a particular way, right? Like there's an activity coefficient model called the NRTL, non-random two-liquid model. So you start off with a fundamental framework of how the fluids interact, and you come up with a functional form, just like Anton's equation. Anton's equation was derived based on the Clapeyron equation, which shows that vapor pressure is exponentially dependent on temperature. Now what we care about is for vapor-liquid equilibrium, we want the partial fugacity of the liquid phase of species I to be equal to the partial fugacity of the vapor phase of species I. So what we have now is an expression for the partial fugacity of the liquid, xi, gamma I, fi, L. And for the vapor phase, generally speaking, we're going to assume that the vapor phase mixing is relatively ideal. So in that case, we'll write yi, fi, v. So now the notation that we'll adopt for vapor-liquid equilibrium, which is going to be the lion's share of equilibrium that we're going to be doing, x is going to correspond to the mole fraction in the liquid phase, y is going to correspond to the mole fraction in the vapor phase. So what is the fugacity of an ideal gas?
The pressure.
It's going to be the pressure. All right. What is the fugacity of a liquid if the vapor phase is ideal? And the system is at relatively low pressure. So we're neglecting the Poynting correction. So what is the most accurate estimate of a pure liquid fugacity?
Saturation pressure.
Saturation pressure if it's an ideal gas, but we can take one more step before that. We can approximate it as the saturated liquid fugacity, which is what you guys solved for in problem 7 of the homework. So this is what we call low pressure vapor-liquid equilibrium. And then lastly, if this is an ideal gas, we get modified Raoult's law. The fugacity of a pure saturated fluid would be equal to its vapor pressure if the pure gas phase fugacity is the pressure. Right? But it doesn't necessarily have to be the case, right? We can take a number of approximations to get down here. So the last step goes back to our mixing here. If we have ideal mixing, okay, which means that we include this entropy of mixing term. Now, if we did not define the activity coefficient, then we would still have a bunch of lingering garbage terms to deal with. But if we have ideal mixing, what does that tell us about the excess Gibbs? That means the excess Gibbs is 0, right? That the actual Gibbs of mixing for the real fluid that we care about is ideal. So that means this term equally cancels out this term, which means our excess Gibbs is 0. So if our excess Gibbs is 0, what is the only way that this expression here can be equal to 0? What does the activity coefficient have to be equal to? Right? So if the activity coefficient is 1, natural log of 1 is 0, 0 times everything is 0. So in this case here, if it's an ideal mixture, if ideal mixture in the liquid phase, activity coefficient is equal to 1, we get Raoult's law. And it only took us like 6 weeks to get here, right? So this very convenient equation that you used probably as a freshman, we very painfully, step by step by step, got to here. This is for a real fluid. We have substituted our expression. So truth be told, going from here to here, what we've actually done, this is an ideal mixture in vapor. Right? It's not an ideal gas mixture, because if it was an ideal gas mixture, then we would have directly replaced the pure fugacity by the pressure of the system. So this is what we're trying to calculate. We have made one approximation. We're saying it's an ideal mixture in the vapor phase. Probably a pretty good assumption. I wouldn't worry too much about it. But if not, you would use the equation of state here, right? You could calculate the vapor phase exactly with an equation of state. We've made one approximation, ideal mixture in vapor phase. Then we assume it's low pressure, which means we can neglect the pointing correction. And if we assume it's an ideal gas, we can replace the fugacity with the pressure for the vapor phase. Then we can write here, if we do another assumption, we can say it's an ideal gas in the vapor. Then that changes the fugacity of the pure liquid. Then we can say it's an ideal mixture in the in the liquid phase, and we can come up with Raoult's law. So Raoult's law is many, 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 many assumptions in the making, for generally speaking. Now this expression here is probably the one that we're going to focus on most likely. This is what we're going to call low pressure vapor liquid equilibrium. Now when we say low pressure, what we're implicitly saying is that the vapor phase is truly ideal. And that's probably going to be fine until you get to several atmospheres of pressure, right? But the liquid phase is almost never going to be ideal. Now the challenge is if you don't do low pressure vapor liquid equilibrium, then you're stuck up here. So non-low pressure vapor liquid equilibrium is extremely challenging because it involves having an accurately tuned equation of state, and then there's really not any fun. You just throw it into a computer program and say, find the solution. Right? So high pressure vapor liquid equilibrium, there is no obvious answer of how to solve problems. It's really a case-by-case basis on which data do you have access to, how accurate are your equations of state. But in terms of educational purposes, so we can start looking at fluid behaviors, we're going to focus on low pressure vapor liquid equilibrium, but we can never assume that the liquid phase is almost ever going to be ideal. Right? Ideal liquid mixtures don't really exist except for systems that are really similar. So benzene, naphthalene, right? That is an ideal liquid mixture. And you can see why. It's benzene, which is a benzene ring, and naphthalene, which is 2 benzene rings. As it turns out, those two get along just as well. They fit together perfectly, they roll, they interact, they're attractive and repulsive in almost exactly the same way. Benzene-naphthalene system is a classic example of an ideal mixture. Another mixture that's going to be almost ideal is going to be 2 N-alkanes. So 1, 2, 3, 4, 5, 6. So let's say hexane, heptane. That's going to be pretty close to an ideal mixture as well. But if I were to mix benzene and heptane, it's no longer an ideal mixture. Right? So even 2 compounds that seem like they're relatively simple hydrocarbons, they'll become a non-ideal mixture as soon as you put them together. So it has to be very, very close in order to be considered ideal. All right. So, any questions? I hope that the importance of fugacity, you may not have, I don't expect you to remember all of this, but what I want you to remember is just the final conclusions. We have to define fugacity. It's annoying because it's a tedious definition on a definition on a definition on a definition, but without fugacity, we would have discontinuities and we couldn't solve problems trivially at all. So when someone asks you, what's fugacity, what's your answer?
Gibbs definition on definition.
Deviation.
So that may be a little bit too glib for a qualifying exam. But in general, it's a Gibbs departure function to remove discontinuities and undefined points that are associated with ideal gas mixing properties. So it is a Gibbs departure function, that's it. That makes it easy for us to calculate Gibbs. All right, thank you, have a good weekend. I will post the homework ASAP. Exam is 1 week from today. So please take a look at the homework soon rather than later so you can have time to study for the exam. All right.
And it's homework